We estimate highly detailed geometry from in-the-wild photographs which can be converted to 3D point clouds. We do this in two steps. In the first step, we estimate a detailed scale and shift invariant depths. A scale and shift invariant depth estimation utilizes abundance of disparity data in training. This leads to a high generalization when used in the wild. In the second step, we provide these robust and highly detailed scale and shift invariant depth maps alongside the input image to a second network to estimate accurate geometrical scale invariant depths. With the highly robust and generalizable inputs, we achieve in-the-wild performance for scale invariant depths, which is otherwise challenging due to the limited available datasets. Our detailed scale invariant depths can be used to project images into 3D point clouds, as you can see in this example. First, let's take a look at how we formulate a scale and shift invariant depth estimation. Vast amount of disparity can be gathered using uncalibrated stereo data from web stereo images or 3D movies. However, as this data is coming from unknown stereo setups, its disparity can be converted to depths up to an unknown scale and shift. Midas introduced a scale and shift invariant loss that mixes these datasets in training, which leads to a high generalization in the wild. Another line of work that also utilizes disparity is ranking-based depth estimation. This method only estimates ordinal relation of pixels in the depth space using sampling-based sparse ranking loss. For each sampled point pair, this loss is defined to push them toward the correct ordering. By comparing these two methods, we notice that a scale and shift invariant depth estimation generalizes well when used in the wild. However, ranking-based methods are able to generate depth maps with more depth discontinuities. To take advantage of both, mixing these two losses is a promising approach. However, even if points have correct ordering, the ranking loss is designed to maximize their differences in the depth space. This can push the points away from their correct absolute differences enforced by the scale and shift invariance loss, which makes these two losses incompatible to each other. Consequently, we introduce our ordinal loss to only push the points toward correct ordering if their ordering is incorrect. This is more clear if we take a look at the derivative of the losses. When the ordering is incorrect, our ordinal loss creates a constant gradient to push the points toward correct ordering. When the correct ordering is achieved, our loss does not create any gradient in the optimization process, allowing the scale and shift invariant loss to be the sole training signal. This way, our ordinal loss creates an extra signal for the training when the ordering is incorrect and does not interfere with the scale and shift invariant loss otherwise. As seen in this example, mixing a scale and shift invariant loss with ordinal loss greatly improves the detail generation ability of the network. Using both losses, we train our network on 8 disparity datasets to achieve in-the-wild performance. We also choose a CNN backbone to be able to use its boostable property. Before moving to comparing our work against the state-of-the-art, let me provide a quick overview on the boostable property of CNN-based monocular depth estimation methods. As we discussed in our CVPR paper from 2021, CNN-based monocular depth estimation methods show different characteristics at different inference resolutions. At the low resolution, network is able to generate a coherent global structure, but many details are missing. At high resolution, however, network generates many depth discontinuities, but the global structure is broken. We show in our experiments that many CNN-based depth estimation methods also show the same behavior and attribute this to the receptive field size of the network and the limited capacity. We then propose to merge these depth maps using a learning-based gradient transfer operation. This results in a detailed depth map with global coherency. Boosted results from our scale and shift invariant network generate significant amount of details and outperform other CNN-based state-of-the-art approaches. Our method also generates more details compared to the much larger transformer-based method used in DPT or the more recent work of depth anything, despite using a much smaller CNN-based backbone. We achieve a highly detailed and robust scale and shift invariant depth estimation in the first step. However, this SSI depth leads to a distorted geometry when projected to 3D. This distortion comes from the shift invariance in the SSI formulation. However, a scale-invariant depth is geometrically accurate and can be projected to 3D without any distortions. However, directly estimating a scale-invariant depth is more challenging due to the fewer available data and the task complexity. As a result, instead of directly estimating a scale-invariant depth, we propose to provide the highly detailed and generalizable scale and shift invariant depths alongside the input image to a second network to generate geometrically accurate scale invariant depths. This way, the network doesn't need to reason about geometry from scratch, and its task is simplified to enforce geometric constraints on the readily provided scale and shift invariant depths. Following our findings in our boosting paper, we separately provide the high-resolution depth discontinuities and the global overall structure generated from our scale and shift invariant depth estimation to a second network. However, instead of using a low-level gradient transfer, we train to enforce geometric constraints using scale-invariant losses on the depths and also losses on the implied surface normals. With the robust inputs, the simplified task has a much smaller domain gap between synthetic and real images. We train our scale-invariant network on a single dataset of hypersim and show that our method is able to generate accurate geometry in the wild. We showcase the application of our detailed scale-invariant depths in 3D photography. Our method can be used to generate accurate novel views and 3D animations of landscapes, or very complex outdoor environments, as you can see in this example, or even an indoor environment with many small and intricate objects. We also provide an ablation to show the necessity of providing our highly detailed depth discontinuities from the scale and shift invariant network to estimate a highly detailed scale invariant depths. Compared to directly estimating a scale invariant depths, readily providing the depth discontinuities leads to more details as well as a better global structure, as the network doesn't need to use its capacity to reason about discontinuities to the same extent. Also, using highly detailed depth discontinuities generated from our mixed sparse and dense training generates more details compared to using other state-of-the-art scale and shift invariant networks. This is because our mixed training strategy leads to a more detailed input that simplifies the task of the scale invariant network more. This also shows that any future scale and shift invariant network can also replace our first step to generate more accurate final geometrical scale invariant depths. Comparing our work to the state-of-the-art shows that methods such as metric 3D that aim to directly estimate scale invariant depths miss many details. This is why our method is able to generate detailed discontinuities benefiting from our multi-resolution two-step approach. Patch fusion uses a brute force patch-based approach that leads to a long runtime and patch boundary artifacts. We generate our consistent high-resolution results in a runtime comparable to other state-of-the-art methods. Our multi-resolution approach leads to modeling of intricate details such as this man's body, while other methods like LeRes, which also employ a two-step approach, fail to recover these details, causing ruptures to the objects in the scene.